All right, and so our next presentation is on the importance of testing and benchmarking. One of the consistent themes you hear sort of about Fido and VPP is sort of the blazingly fast performance that it gives. So we have some folks from the CSIT team, which is the sort of performance lab, performance benchmarking testing team. So anyway, so we will hear about the CSIT continuous performance lab project within Fido. So take it away, guys.
Good morning. I'd like to introduce my colleague, Maciek Konstantynowicz. Maciek is...
He's done it, in Irish accent.
Maciek is the PTL of Fido CSIT, which has been doing extraordinary work in open benchmarking over the last 4 years now, 4 or 5 years now.
Yep.
Maciek is a distinguished engineer at Cisco and has been working on SDN NFV for 6 years.
And I wanted to introduce you to Ray Kinsella, who is a software architect at Intel with much longer experience in SDN NFV than me, over 10 years. And he's also a member of the FD.io TSC.
Yeah, thank you. So I reached out to Maciek a number of weeks ago after a trip to China. Myself and Frank Brockner's, I don't think Frank's here today, but Frank and myself went to China and we presented in Nanjing at a conference. And before that, I had spent a lot of time with customers that we have based in the PRC. And none of them have internet access. None of them provide guest internet access when you're on their site. So, and this was actually a big problem for me because every time I visited a customer, I found myself reaching for the CSIT performance test report that Maciek and team does after every VPP release. Every customer I went to, I reached for these numbers, and dang it, I didn't have internet access. So there was an easy solution for that. I went and I just synced an offline copy of the report. But I stopped there and I said, hang on, there's actually something a bit more fundamental going on here. I'm reaching out and I'm grabbing this report every time I sit and talk to a customer. This is actually, the data in here is incredibly valuable. The data that we're producing here as an open source project is incredibly valuable. And that's why I reached out to Maciek and I wanted to talk about it a bit more. So what are we going to be talking about today? Well, we'll be talking about why code alone is no longer enough, why open benchmarking is so important. We'll be talking about explaining what CSIT is, and then we'll be talking about the continuity problem. The continuity problem we'll get into a bit deeper, but the continuity problem essentially is how do you ensure that your project maintains performance over time? We'll then talk about how you go deeper, how you go beyond just finding the performance regressions to actually finding the help at root causing the performance regressions. And then we'll go to summary at the end. So as Maciek said, I've been working on SDN NFV now for almost 10 years at Intel, and at any given time I've touched any and all of these projects. There's a real galaxy of open source networking projects out there. You know, when I started at Intel, if you wanted to know, most of the time, if you wanted to know what software networking performance looked like, you were benchmarking the kernel. 10 years later, there's a whole galaxy of options out there. And there's so much choice now. There's no real anchor to tell you how any of them really perform. You have no real way of getting an idea of how any of them perform. So you can go and compare performance, and maybe in any given space you might have a number of options. So I take a good example that I've looked at an awful lot recently, which is user space TCP. So you have, I think I counted 12 different user space TCP stacks a number of years ago. Everything from MTCP to TLDK to FStack. And there's no real way to tell, independently how one performs versus another. So, and this posed a question for me, maybe open source is no longer enough. maybe it's no longer enough to put your source code on GitHub. That's only helping your consumer, the person who's using your code so far. So inevitably, when you're looking at any of these options, your next inevitable question is, well, how will it perform for me? I know the features I want. I know that I've identified 12 different user space TCP stacks that might fit my need. How do I know how it's going to perform for me? And then you inevitably end up going down this real rabbit hole of what's the testing methodology they use? Are the benchmarks repeatable? Are they applicable to my test case, and are they vendor neutral? You find yourself reading SDN Central articles. You find yourself looking at blog posts, and inevitably they all have a vendor. They all have a bias. They're all of some kind. And inevitably, particularly with the articles, it's very hard to tell how these numbers were arrived at, most importantly. You'll see a graph, there'll be a bit of text around the graph, but you have no real deep introspection into how they actually got to these numbers. And that really is the critical point here. So, so the situation where we were at was, we had open source, you had a general idea of what the feature set was, but then you really couldn't get to the next level of data of how it was likely to perform for me unless you went and actually did the benchmarking yourself. So I think we actually looked at, how many quotes did we look at to put up? We looked at quite a few quotes to put up here. But I think we both really liked this one. And, there's another one from, I think it's Marco Ringini from Microsoft, and what he says is engineering is a quantitative discipline. If you're not measuring, you're not engineering. And that was originally here, but I took it down. I really liked it because it's similar to this one. It really kind of summed up a lot of what I feel about what we're doing in CSIT, which is that what we're network engineers. Fido, VPP. And all the other Fido sub-projects are an engineering effort. It makes the next logical step on that road is to benchmark the hell out of what it is we do, in order to ensure that we're meeting our goals. So, without data, it's just another person's opinion, and that really is like that stack of data that we talked about in the last slide: the articles, the blog posts, the YouTube videos, they're without the ability to reproduce those benchmarks, without the tools that created those benchmarks, without the methodology that produced those numbers, it really becomes very hard to tell how those numbers were arrived at. And that's why we say, bring data. How did you get to this data? Where is the transparency?
So just an aside, we actually had quite a few more quotes which were going to more, philosophical, but it was all coming down to actually how do you verify experience, and get a user perspective or a spectrum of perspectives based on data. And I guess in the next revisions of this, we're gonna cram a few more quotes. But that's a good warm up. Go ahead, Ray.
I like this one. I thought this one would work.
Yeah, that's the best one. There's a single one. Yeah, that was our constraint.
So, for those who are not familiar, who's familiar with Fido CSIT already? Okay, so about 40% of the room.
Brian, only that?
Yeah.
You are building a test bed, for Christ's sake. Come on. I know.
So, at CSIT, everything we do is open from the grounds up. It's an open source, collaborative community in the very best sense. We use open tools that anybody can get their hands on. Tools like Robot, tools like T-Rex, and Jenkins. These are tools that everybody in the room is familiar with. We use open standards like RFC 2544, standards that everybody is familiar with. We do simple, we build complexity through starting simple. We do single core tests, we do dual core tests, we do multi-core testing. We go for partial drop rate, we go for non-drop rate. So we really build up a huge corpus of test data. We go after we benchmark many popular test cases like L2, L3, at L2 we benchmark things like VLANs, Q&Q, we test things like input ACLs, at L3 we test things like routing, we test things like network overlays, we test things like our vhost implementation. Really, we test the real network primitives, the real things that are really incredibly important to make sure are right in order to get a good performance experience. The really critical thing about CSIT is a fully open environment. If you don't have confidence in how the numbers were arrived at CSIT, we give you everything. We give you all the test tools. We give you all of the documentation that you need in order to reproduce the environment locally and rerun the tests locally so you can get the same numbers locally. So when you're grabbing our performance report, you know exactly how the numbers were arrived at. And this is the real critical difference between CSIT and maybe a white paper or something like that. Whereas a white paper, you don't have that level of transparency. You don't have that level of introspection. In CSIT, we're giving you everything that you need to get to those numbers. And then most importantly, we're multi-platform and we're multi-vendor. We have both Intel and ARM hardware now in CSIT. So it's, the real effort is to make sure that we're benchmarking on a number of platforms so you have confidence in how it's performing across a number of hardware platform vendors. Some stuff that I failed to hit. Oh yes, we hit multiple operating systems, and Marco Verlazy sitting over there from SUSE. So we test on Debian, CentOS, Fedora, SUSE. Have I missed anything? No. No. Okay. Perfect. So, everything in CSIT is completely automated. So, and very integrated into the Fido development experience. So when you submit a patch to VPP, that patch automatically has unit test cases run against it. There's nightly performance regressions so that we know over time whether performance has regressed over time. We have automatic builds to tell, hey, this is built correctly. But not only are there automatic builds, but as I said, there's unit testing to make sure this thing is behaving correctly. But then we also have a larger set of test cases that run nightly to tell, hey, the function hasn't been affected during the commits over this day, and performance hasn't been regressed over the commits from this day. As I said, we have functional test cases and we have a large battery of performance test suites. One of the most valuable thing, and the thing I was reaching for in the PRC the whole time, is the performance test report that we produce after every release. So this covers everything that you might imagine. It's exhaustively documented and it has real detail in it about how all of the core test cases are performing for each in each network function in Fido VPP. There are use case driven. There's use case driven testing. So it's not just we do the kind of lower level stuff like how L2 hangs together, how L3 hangs together, and then we actually put the show together. Like we put L2 and L3 with vhost and see what a real NFV scenario looks like. We put MEMIF together with L3 to see what a real cloud scenario is actually benchmarking like. So we do the simpler test cases and then we do the more sophisticated test cases to understand what performance will look like in an NFVI environment, to understand what performance will look like in a cloud native environment. And then finally, I said well, about the integration into Fido CI systems. But I want to touch on it again because the integration with the CI system is the Fido continuous integration system is what allows us to catch regressions as they happen. You know, and this goes back to what Marco Rangrini said about engineering being a quantitative discipline. You know, when we submit a patch, you know, or when we add new features to Fido, we don't want a lottery. We want absolute determinism that we haven't impacted performance adversely. And we're going to talk about that in much more depth in a moment.
So just to summarize, in terms of the goals for the CISIT, and the CPL suffix stands for Continuous Performance Lab, are three things. Conformance against the specs, like IETF RFCs, we're dealing with networking. Performance, Ray talked about that. And efficiency, how well we're actually using the machine in terms of the core cycles, in terms of memory, in terms of I/O, and in terms of, at the end of the day, the power and the footprint. So efficiency, basic efficiency metrics that then translate into the, you know, the ROIs, the TCOs, and the efficiency of the overall platform. So three things: conformance, performance, efficiency.
So I made reference earlier to the per release report that I was reaching to when I was in the PRC, and I wanted to give a little bit of a flavor of what you will typically find in this report, because this has been the real stalwart of what Fido CSIT has been, you know, of their activity. You know, it was single platform till now. It'll be multi-platform multi-vendor quite soon.
Once Brian builds the ARM testbed. Brian? Good.
We do both packet throughput and latency. So in a lot of cases, you will see only, whenever you read articles from elsewhere, you'll only see throughput numbers. It's less common to actually find latency numbers. And in fact, in the world that I live in, latency numbers are imperative. If you talk to any wireless vendor, anybody who works in any cellular vendor, latency numbers are imperative. We benchmark both VPP and DPDK. DPDK in VPP is an incredibly important ingredient. So it's very important for us to understand the performance characteristics of DPDK. Right. And to be fair, the DPDK team helped us get the bootstrap some deep testing in Fido CSIT. So we regularly benchmark, and the performance of both VPP and DPDK is as a key ingredient for VPP. We do single core testing, we do multi-core testing, but we also do scale testing. And this is somewhere where Fido VPP really shines, is we do, I think if I remember, we do something like, we do a single flow, we do 20,000 flows, we do 200,000 flows, and then we do 2 million flows at L3 to understand how performance is affected and what scaling looks like across a very large number of flows. Because that's what real networks look like. Some real network test cases have very large numbers of flows. So if you're not testing with large number of flows, how do you know how it's going to perform? Same with ACLs. We do testing with one ACL, and then we scale out ACLs to 2,000 ACLs to see what it looks like. So everything we do, we test at scale. Single core to multi-core, small number of flows to large number of flows, small number of ACLs to large number of ACLs. Understand how performance is affected. And then we have a very, very large corpus of test cases, up to 100 performance test cases, 173 at this point, across L2, L3, including things like network overlays. We test things like critical pieces of infrastructure like MEMIF for containers and like vhost for NFVI. We also test cases like crypto acceleration. We have an accelerated IPsec implementation now in VPP. So we touch other pieces of hardware just than NICs. We touch things like crypto accelerators as well. And then we test things like overlays like segment routing v6. I'm sure I'm miscategorizing segment routing v6 as an overlay. I think we have presentations on that later. And this is very typical of the kind of data that you get out of CSIT. You know, you can see the first test case there is a 2 million route IPv4 scale testing. The next one down is the IPv4 base test. So you're comparing IPv4 with a single flow to IPv4 with 2 million flows. And you can get the idea. This is how it performed in VPP 1801. This is how it performed in VPP 1710. This is how it performed in VPP 1707. So you get a real idea over time how performance is trending. So it's all about breadth. We have a huge number of test cases, all about depth, understanding why the test cases are performing as they are, and understanding when we have regressions. And it's also about predictability. It's a predictability performance, but it's actually, we're doing this on a cadence. We're doing this every night. We're doing this on every major release. It's a quantitative discipline. Are you measuring? Do you understand what your performance is like?
That's right. So just about the number of tests, these are the base root tests, and then we're going through a number of combinations of packet sizes and offered loads, and you know, multi-core and multi-thread configuration. So the number is actually much higher in reality than that. But a good summary, Ray. Thank you. All right. So we are, give or take, halfway through the time, and 1/3 for the slides. So. And it's technically break time, so how much time do we have left, Heather? Half time, yes? Yeah, I was going to say. Half time.
We can keep going. We can keep going. I mean, basically the schedule is hours for the day. Excellent. And we can just maybe have slightly shorter lunch.
Can I say in my defense, they usually have a big clock in front of me.
Yeah. Well, I can start holding up like little cards that say 5 minutes left, 10 minutes left.
But hopefully everybody is getting woken up. It's still Monday morning local time and the UK time where I'm from, despite my name. So the continuity problem. Ray has introduced it already. And we're going to do a bit of a deep dive into that, but we will ease into it gently. Leaning Tower of Pizza, thank you, Ray, for an excellent illustration. You know, we're building a system, and it's going fast right now. It's developing fast too. How do we make sure that the higher, the faster we go? We don't go and lean into the wrong side, and you know, fighting with gravity is not easy if you are leaning. So how do we manage to actually keep making sure that the software stays top notch, and it does the best in class, and as we call it some folks call it in technical marketing material, best on the planet software data plane. And keep adding features and keep taking advantages of the new software efficiency techniques, compiler efficiency techniques, and also latest, greatest generations of hardware and hardware accelerators. And how do we prevent harm? And how do we provide a guarantee in terms of performance for a long term? So I'm going to hit you with some graphs. They are machine generated, so they're not the most pleasant to the eye, but we're getting there. And visualizing what we want to show is hard. So this is something we have just launched. It's been actually published for a while, but the announce email went out last night from the Radisson Hotel just across the river from here. We do performance trending. We, as a project, we are continuously testing, and we're going through all of those tests that Ray has referred to that go into the report. But in addition, we do test daily, and we publish the results, and then we do some calculations, some trending calculations. So we calculate the 7-day trend line, and then we use very simple calculations and algorithms to pick up anomalies. When things are staying horizontal, which is good. When things are going up, progressions, green circles. When things are not going well, regressions, and then we're picking up some anomalies. We're doing a quick brute force tests where we basically bombard the system with the line rate of packets, and we measure how many go through, so that we don't do any searches. We just verify the best case scenario of how many packets the system can handle. Still, it's a lot of data to analyze. We have right now about 252 graphs of that sort. So we don't expect humans to be looking at 252 graphs every day. So how do we make humans to analyze this data and also feed it to higher level systems? Well, we summarize. So we produce a dashboard. Again, dashboard is published, where we basically per test case publish the trend, the weekly trend. We then do some short-term and long-term trend change calculations, and we list number of regressions, progressions. And of course, we want to first bad news travels fast, so we list the regressions at the top. Then we reward the greens with progressions, and then we list the rest. So that way, we feed that to the community, and we want a VPP community and FD.io community to looking at this, if not every day, regularly, and we'll be reviewing this on the community calls. And of course, we want to keep the rats in check, and we want to allow greens to grow as much as they can, because that's what will prevent the Tower of Pizza from leaning. Some of the challenges we have, getting the C rate is not easy, as it seems, because all those tests are actually requiring a real hardware. Believe it or not, but which was a shocker when I attended the cross-CI workshop at ONS in LA a few weeks back. We found out that we are the only project in LFN ecosystem, LFN umbrella, and I'm not sure if it doesn't apply to all of the LF, that requires to run on real hardware. We can't run performance on a virtualized hardware. So we are clearly restricted by physical resources. And those tests use those resources, and they take time. So we are restricted to what we can do and the frequency. After being alive for 2 years, we're learning and we're getting smarter. We're getting smarter with test methodologies and algorithms, and we are watching very closely the efficiency of the execution and also type of tests we run. So, as I said, right now we are executing those trending tests on the regular basis, twice a day at the moment. We are giving the developers a way to trigger the performance benchmark tests on a per patch. Going forward, as we are building a new lab, thanks to LF, we will have enough hardware pool to be able to execute performance tests per patch and trend it that way that I showed. And we want to maintain this feedback loop to the user, to the developers, to the users, and to the committers. And also, we will be feeding it to the trending analytics tools to keep monitoring the developments and the trending. So, on those charts, I encourage everyone, existing committers and contributors, and the new faces, to give us feedback. Feeding the sort of multi-dimensional information into humans in a sort of applicable and spot-on form is not easy. So it's a navigation for the systems that actually makes it happen. And actually, when you click on those tests, you are navigated to the right charts, to the right VPP builds, and to the right test logs. And we're gonna keep improving that. So, few words about the efficiency. And as Ray is actually saying in the subtitle, we are moving beyond the symptom. We want to understand what exactly is going on the machine, and nobody can tell us. So we need to measure. And somebody from the expert developers who's been working on DBP for a while keeps telling me that, you can talk to all these processor architects and micro architects and all the gurus who build this hardware. But the fact is that for more than 50% of the time, nobody knows what the machine does. Why? Because it's real-time prediction and sequencing, and nobody knows. So unless you measure, you don't know. So how do we measure? Well, we went back to the computer science textbooks, Mr. Henderson and Hennessy, Kenderson and Hennessy, and we basically worked out the basic metrics to apply for the packet processing efficiency. So we're just taking the units of work, which is a packet. We measure time used to process the packet, and then calculate a set of internal and external metrics: the clocks per packet, and the instructions per cycle, cycles per packet, instructions per cycle, and then the usual networking external metrics: PPS, packets per second, and bits per second. And then we look at the the modern machines. This is just a depiction of the Xeon server, 2-socket, and we look at these 4 points and understand which of these matter from packet perspective, and how do we correlate the resource utilization to the CPP, PPS, and BPS metrics. We then use a bunch of open source tools. And I'm pleased to say that FD.io gave us an opportunity to work with across the multiple vendors, Cisco, Intel, ARM, others, and networking companies, hardware companies, and we actually innovate. Those tools, believe it or not, thanks to FD.io, have been beefed up. And a number of Intel vTune technologies made its way to the PMU tools that have been already there, but they've been hardened and updated to cover Skylake. And you can do everything. We can do everything we need with those open source tools, and they give us the insight we need. So, what insight are we after? We showed these graphs. We're going to be producing more fancy graphs going forward. Communicating visually is usually the best way for multidimensional information. These charts come from the white paper that we have published as part of the FD.io collaboration between Shrikant, Patrick, and myself. Shrikant and Patrick are from Intel, and we want to make people understand that the packets per second performance is actually directly correlated to the cycles per packet. The lower the cycles per packet, the higher the MPPS. The lower the cycles per packet, the higher the MPPS. The lower cycles per packet, the faster the machine goes, the more services you can cram, and the less power and core usage per unit of service or happy customer. Important metric, a baseline primitive. And then we go even deeper. And that's a traffic light system that we have envisaged over 2 years ago. And we want to use, in this case, a Xeon Telemetry Analytics, which is a hardware counters on processors. The similar thing exists for ARM and other processors. And we want to actually illustrate on how well digging deeper on where is the CPP coming from, and if CPP is high, why is it high? Which parts of the system are not used correctly? The main metric here is, I won't bother you with all this bad speculation and all the other naming, but the black line, the instructions per cycle, the IPC. If you know what a CPU is, Alan Turing von Neumann CPU, the ALU, it does instructions. Well, modern processors have many of these. They have a pipeline or a parallel set of execution engines that can do the instruction at a time. And the latest one, the in Xeon land, Skylake, has got 5 of these. So it can actually theoretically execute up to 5. Actually, practically can execute 5 instructions. This machine that is listed here is Broadwell. It's got 4. So what we list on the left we list a core mark, which is the HPC, high performance computing benchmarking workload that runs from L1 cache, LI instruction and data. And you can get to 4, a theoretical 4 when you do empty loop. i.e. machine doesn't do nothing, it doesn't do anything, and you get the theoretical 4. Practically, core mark for us is a reference on what actually is practically achievable if software runs from L1 cache, which is artificial. So you can see that the core mark here with hyperthreading is around 3.2. Okay, 3.2 instructions per cycle out of theoretical 4. Not bad. Huh? VPP comes close to 3. And you can see the curve. So the curve itself is showing that certain workloads on VPP, and VPP IPv4 routing today is the most optimal performance path tuned. And this is with 1 million IPv4/32 prefixes. Gets that high. So close to the HPC workload that runs from L1 cache. And of course, we can't fit 1 million routes into the L1 cache. So not bad. Not bad. Not bad at all. And that's what we want to paint going forward. We want to give people the awareness of how their code performs. And even though they may not understand all of those metrics to start with, they will understand the first one. And as they learn, they're going to understand the rest. It's not rocket science. It really is not rocket science. Well, maybe a bit. All right. Ray?
I suppose just to close, to restate what I said at the start of the presentation, it's just open source is no longer enough. Open benchmarking naturally follows. And that Fido CSIT is, really leading in the space in terms of the breadth and the depth of the data that we actually provide in Fido. And this has really immensely, positive benefits for the Fido sub-projects that engage in CSIT, and we can really see it reflected in the performance of things like Fido VPP. Our next steps is to keep addressing the continuity problem, to make sure that, and really the key for the continuity problem for me is making sure that we don't lose performance is like a death of 1,000 cuts. You need that certainty that every patch that gets added to the software, you're not losing your performance with every patch. And that's really where the key value of what Maciek is describing, the continuity problem is. It is that safety net that we introduce into the continuous integration system to ensure that our performance is maintained with every patch, with every nightly regression test, and with every release that we do. And then finally, it's about bringing more data. It's no longer measuring, continuing to measure the symptom, but then actually going deep and understanding the source of the problem.
Thank you, Ray. And I'll encourage you to refer to the white paper that's published at the FD.io link that does introduction to the modern computing and modern software data plane, and then goes deeper and deeper into the topics that we have discussed. And there's also a talk we given in Austin, KubeCon, FD.io Mini Summit with the authors. So with that, I think that's a good summary.
We may have questions.
Maybe a few questions.
We may have questions.
Are there any questions? Here,
Of course.
Sure.
Yeah.
We can share the mic.
All right.
Hey, I really like this. I really like the next steps. I want to dig a little bit deeper on a couple of those. So I really I agree it's totally important to do the checking on every commit, right? Because that's really what you have to do. So I want to express appreciation for whoever's given the hardware. My gosh, that's huge. I mean, round of applause. I think so are you going to be doing all the checking on every commit, or just some of it?
The reality today is we don't have enough testbeds to do per commit automatically. Okay, so
but you said that's coming. Someone's making new.
That's coming. So today we are executing those tests twice a day. So we cut the commits into the batches in 12 hours time. And if you go with the links, we actually test at 2 and 1400 UTC. Okay. We're just in the process of building new labs. Thanks to LF, we got a budget. We bought, quite a bunch of hardware, 20 state-of-the-art Xeon Skylake machines with a lot of I/O. In fact, they are so hot that we can't. The manufacturer cannot ship it to us because somebody is eating them for us. It's Azure and all the guys who do AI, because they are the only motherboard in the market that gives the maximum I/O into the PCIe. But they are coming, and they're actually building this week. So we're going to have quite a few more testbeds, and that will give us a way to execute on a pay per patch. We will not be executing all tests, all those 173 plus combinations per patch, but we'll be executing the tests on the code path affected by the patch. And that is hopefully be achievable in the release 18.07. So 18.04 BPP shipped last week. We are doing the report right now. The testbeds are busy doing the test for the report that Ray has referred to. It will be auto-generated about hopefully Wednesday, Thursday, and then we're starting the work on 18.07, and that's the goal. We have pretty much all the software infrastructure is in place. We're waiting for the new hardware, and we want to grow it. And we're going to apply exactly the same to the ARM testbeds that are being built. Brian, just behind you, can comment on what's coming on ARM front. There is quite a few different servers and ARM processors being built. So that's the current trajectory. But we always need help. So
Get
if you're
involved.
interested,
Get involved.
Thank
Get
you.
involved.
You
Get
just said
involved.
something that added to my worries on the second point. In terms of digging deeper and understanding.
Yep.
So the tests, are they testing a machine that is only running the test? I mean, most machines are running some workload as well as the test.
Yeah. Very good question.
And also, you just mentioned motherboard.
Yep.
What about those of us who don't have the greatest motherboards?
Yeah, sure. So the way we're approaching, so there are two questions there, right? Workloads first. So we do tests on, bare metal test, vSwitch-like tests. So we do packets between the NICs, okay? PCI, using the Intel DDIO, for example, goes to the cache. BPP does the magic, or SPMD does the magic, and loops back. So it's between the NICs. The other set of tests, we test vhost and VM. So on the KVM hypervisor, we go vhost user into the VM FD.io. We do run a workload in the VM that just loops packets or does something to the packets, and then spits them back. Right now, the main workloads we're running in the VM are the DPDK test PMD workload. So
What is that?
It's the DPDK-based Polmo driver thing that loops the packets between the FD.io interfaces.
Right. I mean, my concern here is typically real workloads don't just do networking; they have other stuff that hits the L1 cache.
Sure. So that's for the VM. For the containers, we have a similar setup with VPP in a container, but we do not currently test any other workloads. That's something that we are interested to do.
So indices is set up, and we've done a really good job of isolating the machine to make sure that there's only what's run, what we want to measure is run. So we do things like we do kernel configuration, we do operating system configuration to really reduce down to make sure that we're only measuring what we're interested in. The other thing I'd say is you mentioned that we're not running the latest and greatest hardware. We make in the CI infrastructure, a software engineer, before submitting a patch, can run his or her patch in the Fido test lab to get an idea, to have the Fido test lab generate the numbers and tell you what the performance is looking at. So if you don't have the latest and greatest hardware, or most importantly, if you want to understand how it performs in the Fido Open Lab, you have hooks in order to generate those numbers from the lab and get those numbers back.
I'm sorry, I'm going to put it the other way. Not from a developer's point of view, but from a deployer's or consumer's point of view, right? what use are these numbers to me if I want to run it on not the greatest motherboards?
Okay. So quick comment to what Ray said, and then I answer your question. So we actually do know what we measure. We constrain the resources used by the software device on the test. The rest of the machine is not used. So the other cores, the other L1, L2 caches, and parts of LLC are not used. Same for memory.
So the key idea here is you're dedicating cores, so it's okay to dedicate the L1 cache.
Yes. So that's the resource isolation. Now, how do you apply what we measure to the actual much wider set of use cases? Different motherboards, different processors, different number of cores, different levels of cache. So the way we go about it is, and actually it's all explained in the white paper, we do profile the scaling. The scaling depending on the processor frequency. In addition to different processors, you have a scaling in terms of scale up in terms of frequency. You have a scale up in terms of multiple cores. You have a scale up in terms of using hyperthreading or not using hyperthreading. And based on that, you arrive to a set of basic metrics that you can use to extrapolate to a much wider set of use cases. So if you want to use cores of different frequency, but you know what those cores are in terms of processor type, you will be able to extrapolate based on the profiling done onto how you should expect this to work in your environment, if that makes sense.
You didn't mention scaling for different motherboards.
Motherboards do not matter that much. The only thing I emphasize on the motherboard for our lab is that we wanted to have as much as possible of I/O, because FD.io as a software data plane can actually fill it up. So we wanted to show that on the processor, on the currently shipping processors, you can get to the terabit speeds. That's all.
We actually exhaust the PCI links.
That's the only dependency on the motherboard. And by the way, all those motherboards ship with with a processor manufacturer chipset. So in this case, Intel. It's just that the OEM who is building, a vendor who is building those machines, makes choices about allocating this much to PCIe, that much to the disk, and so on. So that was the only dependency on the motherboard. Okay.
All right, so we are now officially about half an hour behind schedule. Yay, us! But there are lots of great conversations. So we are actually now up at break time, and I sort of encourage folks to kind of continue these conversations over some snacks and caffeine.